There can be an infinite number of dimensions. And when Einstein heard about it, he did not like it at all. He regarded this as mathematical sophistry. Without that picture, general relativity would be dead. The mathematics has its own existence. We don't create it, we discover it, or we discover parts of it. It would still be there if there had been no human race. It's so elegant, powerful, universal, and beautiful that they think that the physical world must operate. It's very abstract, but nevertheless it is very permanent. When I take the view that mathematics is out there, it's not a creation of ours. It's more like archaeology than you might think. That is to say, you dig and dig and dig and you're trying to find some result in mathematics. And in a sense, it's there all the time. Even if nobody had ever seen it, it's still there. So it has a reality. This is a mathematical theorem, some result in mathematics, which may never have been come across by human beings, but nevertheless still has its own existence. So I take the view, which is very common amongst mathematicians, that the mathematical world has its own existence, which is independent of us. We don't create it, we discover it, or we discover parts of it. When I try to think about mathematics, it's a very visual process in my case. Either way, the mathematics has its own existence, which is not imposed upon the world by us. It's there already. So as I said, it's more like archaeology than I think most people would think. That you can dig and dig and dig, and then you find something hidden in the rocks, some skeleton or something which you didn't know was there before, but it was there all the time, even though nobody was there to try and find it. So these results are there. Sometimes we're lucky enough to find one. Sometimes some of these are more attractive than others. Some of them are more powerful than others. Some of them are more universal than others. Some of them more just elegant than others. Would still be there if there had been no human race. I don't think of it as subjective. I mean, whether you can see it as a truth is very subjective. You may understand why it's true, and that could be quite subjective. I mean, usually you have some sort of thing called a proof in mathematics, some argument, sequence of steps, and you agree that each of these steps continues to give you truth, and then you end up with the result you want. And you can follow the steps and say, I see why it's true. You see, may you have some way of seeing, but you may have another way of seeing why it's true. You may have another way which you regard as superior to the other way. And these judgments are very personal and subjective, but the objective truth of this fact, say that 2 + 1 = 3, is independent of us. It's there. I could say set in stone, but if I say it that way, that's a little bit too concrete on the one hand, and too artificial, because it depends on the concept of a stone, you see, which is not so permanent as a mathematical idea. So mathematics it's very abstract, but nevertheless it is very permanent and has an existence which is independent of us. Well, the physics of the world, that's in this picture. I don't think you referred to it as yet. I have this picture of the three worlds with the sort of three blobs. And each of these worlds, the one at the top I usually represent with the world of mathematics, which has its own independent existence. Then there's a world of physical behavior. And then there is the connection between the two, is how the laws of physics seem to be governed by mathematics. And not just any old mathematics. It tends to be mathematics with a particular character which is very universal and has its own internal beauty. Now, of course, you may judge the beauty to be a personal matter, but there is something very intrinsic to the mathematics, which is not very much a personal matter. It's there independent of us. It's hard to describe that, but you certainly find that the more you understand about the operations of the physical world, how it operates, how it behaves, the more we see how it's dependent on mathematics, and not just any old mathematics. It's very subtle, sophisticated, and global in its character, so it has a very universal character. Some people try to argue the other way around. They say if they have a beautiful theory, a wonderful theory, or a sort of universal kind of theory, therefore it must be true as the physical world. And I find this a dangerous point of view. There are people who hold such views, that the mathematics they've come across is so elegant, powerful, universal, and beautiful that they think that the physical world must operate in accordance with those rules. And I say, not a very good test. The other way around, yes, I do believe. That is to say, if you do find something which works very well in the physical world, then you find, for some reason, that it has this universality, this beauty in it, attractiveness in ways that we hadn't anticipated originally. And you see in Newtonian mechanics, you see Newton starting with the laws of gravity, which came from Kepler. Of course, Kepler had this, and some of the basic laws which came from Galileo. So Galileo and Kepler, and Newton formed this into a general theory. And he treated all sorts of laws of force which you don't see in nature necessarily, but he treated them as a part of the general scheme. And out of this general scheme grew some general formalisms which were not anticipated by Newton explicitly. People like Lagrange and Euler discovered ways of describing these laws in more general terms. And so you could describe physical behavior in a very, very general way. Even so, you had to be careful, because these laws turned out not to be as universal as had seemed in two respects. One of these had to do with quantum mechanics, and the rules of quantum mechanics, although they are tied in with the Newtonian laws and very much without the Newtonian mechanics and also the kind of Leibnizian way of looking at Newtonian mechanics, one could not describe this development into quantum theory. So quantum mechanics was not the same as Newtonian mechanics. It has very different rules within it, which are very mathematical, but not quite the same mathematics as had been useful in Newtonian mechanics. First of all, in quantum mechanics, you talk about schemes which are not three-dimensional. They're not four-dimensional. They can be n-dimensional. They can be infinite number of dimensions. And it's not that our brains are tuned to 3 dimensions and therefore we cannot cope with these higher dimensions. It may be more difficult. You may think about it in ways which are not so visual. Often visual thinking may be regarded as somewhat limited in this respect, because 3 dimensions are the way that's most natural for us to think. However, let's not even talk about Einstein, you see. It was the theory of special relativity which was developed by Einstein in particular, but many of the ideas predated Einstein. I mean, Lorentz, people came before Einstein, and most particularly Minkowski had this way of describing the special theory of relativity in a very geometrical way. And this geometry is not 3-dimensional geometry, it's 4-dimensional geometry. Now, this way of looking at special relativity is a revelation. It's much easier to think about the laws of special relativity in terms of Minkowski's 4-dimensional scheme. So I'm sort of disagreeing with this point of view that we can only think visually in 3 dimensions, because we have to think in 4 dimensions. Of course, we may use little tricks, which is the way I tend to do it. I like to think 3-dimensionally, but then I think of a picture which is meant to be 4-dimensional, and I have ways of thinking about it, which I know are inaccurate in certain ways, and I know how to deal with that. I think of these little cones, for instance, and I know I can picture the cones, and the cones, you see the picture, in fact, I'm thinking about is, although three-dimensional, it's not Euclidean three-dimensional. You see, Euclidean three dimensions has 3 dimensions which are all on an equal footing, left, right, and up. And they're all of a similar character. However, when you try to think about general relativity or even special relativity, the thing to do is to think of 2 of them as space and 1 of them as time. So you may think of a 2-dimensional space and a 1-dimensional time, and you get a good geometrical feeling, which is not Euclidean, because the time dimension behaves in a different way. There's a sign, it's very algebraically similar, but there is a sign which is a minus rather than a plus. And they differ in that quantum mechanics was the product of many, many different thinkers. And general relativity was primarily Einstein alone. When I say alone, that's not quite fair. Well, there are certain ironies. You see, one of the big irony altogether is Minkowski. You see, Minkowski had this way of understanding special relativity. I'm not talking about general relativity. Special relativity did not need Einstein for it to be discovered. There were many people who contributed to special relativity. Einstein perhaps had a better overall view of how the thing fitted together, E equals mc squared, this famous formula of Einstein's, was a very important feature of special relativity, and Einstein was a major contributor to that theory. But in a certain sense, he was a little bit what one might call I'm trying to think of the right word, reactionary almost. You see, he had a way of looking at special relativity which was in terms of observers, and how different observers would transform the picture into each other. And you look at these transformations from observers, and somehow there wasn't a real world. You see, the word relativity is a bad word, but we think about the world in different ways, and they are relative to each other. They don't give you an overall unique picture. There was a relative way of looking at the world. Minkowski spoiled that picture, you see. He introduced this 4-dimensional picture of special relativity. And when Einstein heard about it, he did not like it at all. He regarded this as mathematical sophistry, or some German word which I have given the translation, but something like mathematical sophistry. It's not real physics. It's mathematics playing with it and making it look like nice mathematics. Not really real physics. However, Einstein had to change his mind, because when he developed general relativity, he would not have made any headway without having Minkowski's picture. So Minkowski's picture, when you make it curved rather than flat, that gives you general relativity. But you have to have the flat version already in your mind, the flat version of 4-dimensional space-time. Without that picture, general relativity would be dead, or I say it would never have had the breath of life breathed into it. It would not have existed. Einstein would not have thought of it. He needed Minkowski's picture. Despite his just being dismissive of it originally, he came around to realize that this was the right way to think of special relativity, and yet you can then go beyond it and talk about what he called general relativity. Nevertheless, the names are rather confusing. It's the name of relativity still conveys the idea that it depends on your coordinates, or you have different ways of writing it down. It doesn't suggest there is a real absolute quantity out there which you are describing. And that is the real way to think about general relativity, is not in terms of a relative set of different viewpoints. It's one geometrical object which you can maybe understand that way. Once you've understood it, whatever way you try to choose to understand it, that way gives you a picture of the 4-dimensional space-time. And you ask me, can you visualize it because it's got 4 dimensions rather than 3? Well, we can do a pretty good job. I find I'm not too bad at visualizing. Maybe I use little tricks, and I use tricks by thinking of what 3-dimensional case looks like, what 2 plus 1. See, when a 3-dimension, it's not Euclidean 3-dimension, it's special relativity 3 dimensions, where the time is different from the space. And you see, when you do a rotation in 3 dimensions, you see, say rotation in 2 dimensions. I rotate my frame, I've got 2 axes, and I rotate it round.